Hi everybody, today we're going to go over some questions from section 2.1 in the practice of statistics. I'm going to take a look at questions number 1, 3, 9, 15, 19, 21, and 23. Okay, for number 1, we have a thing about shoes. We have a distribution for 20 female and 20 male students at a large high school. It's talking about how many pairs of shoes they have. I'm just going to do part A and then kind of talk about B and C. So I went ahead and listed all of the females' shoes in order because that's kind of where we need to start. The question is, what's the percentile for the female student with 22 pairs of shoes? Okay, kind of depends on if we're using the old definition or the new definition of percentile. The old definition says it's the percent that are less than that number. 1, 2, 3, 4, 5. There are 5 that are less, so it would be 5 out of 20, which is exactly 25%. That's the old definition. If I go by the new definition, it says it's the percent that are less than or equal to, so I would include the 22. So it would be 6 out of 20, and that would give me 30% instead. So for the boy, what we can notice is that the numbers are a lot smaller. I don't feel like writing them all in order right now because it's a lot, and we want to keep covering the rest of the questions. So, but you would do the same thing. And the thing is, even though both the female and the male have 22 pairs of shoes, the female is only in the 30th percentile and the male is in like the 85th or 90th percentile. It's like way higher. And so if I was kind of comparing them, I would say that the boy is more unusual than the girl is because the girl has a value that's closer to the middle and the boy has one that's closer to the upper end. Question number 3. Josh got the results of a statewide Algebra 2 test and his score is at the 60th percentile. When he gets home, he tells his parents that he got 60% of the questions correct on the state test. Explain what is wrong. Well, he could have gotten a 50% on the test and done better than 60%. He could have gotten an 85 on the test and still done better than 60%. So the percentile is saying how he did relative to everybody else. Really, it's a relative location. So his score is better or the same. If we use the new definition, it would be better or the same as 60% of other students in the state. Question number 9 is kind of a beast, mostly part C. If I wanted to estimate the interquartile range of this distribution, I need to figure out where the 25th percentile is and where the 75th percentile is. So that's Q1 and Q3. So I'm going to start on the y-axis and do my best to get it about 25%. And then I'm going to go down. Notice that falls between 10 and 20. And I don't know, maybe that's about $19. Q3 is going to be the 75th percentile. So on the y-axis, I'm going to go try to be in the middle of 70 and 80. And then I'm going to go down. That looks to be at maybe 45 or 46. I think your book estimated 46, but it's an estimation. It would be close. So that means the IQR is going to be 46 minus 19, which is going to give me $27. So that would be my best estimation of the IQR. That's number part A. Part B, what's the percentile for the shopper who spent $19.50? So I'm going to go to the amount spent. I just said that 19 looked like it was at the 25th percentile, so 1950 is probably just a little bit more than that. So maybe the 30th percentile, or between the 25th and the 26th. I don't know, we're estimating here. I would say like 26th or 27th percentile. Okay. Here comes the doozy. So I'm going to erase these marks so that I can see what's going on. If I'm wanting to make a histogram out of this, and honestly, I'm probably just going to like partially make a histogram. But if I wanted to make a histogram of this, I would, first of all, make my x-axis match their x-axis. So I'm going to, down here, I'm going to have, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay. Trying to squeeze those in there. And those are dollars. And I'm also going to have percents on the y-axis, but the thing is it's never going to get as high as 100 because the cumulative one, it's adding all of them together, it's giving you 100. If I'm just trying to see what percent each individual thing is. I'm basically trying to figure out what percent each interval is. So I'm going to spread these out a little bit more. 10, 20, 30, 40, 50. These are going to be percents. Okay, so between 0 and 10, let me kind of focus on this one first. Between 0 and 10, it kind of looks like there's not quite 10, more than 5, I'd say maybe approximately 6%. So I'm going to make a bar between 0 and 10 that is maybe about right there. So take a look. If you see my black bar down here in the corner, it's a little bit more than 50%. So then I need to figure out how much this is, basically. It goes from what I'm thinking is about 6% to about, I don't know, a little less than 30. It's really hard to tell. So maybe 28. So if this is going, let's say this is at 28. If that's at 28 and I started at 6, then that means that this piece is like 22% tall. So I'm going to do that here. So between 10 and 20, I'm going about 22%. Okay, now remember, I'm trying to mark as I go here. I estimated that this was about 28. This one looks like it is about 60. So if I subtract those two, that gives me 32. So that means that like this space right here was 32%. So my bar between 20 and 30 should be about there. And then we just keep going. So that dot was at 60. This next dot looks like it's at, I don't know, 60. It's so hard to tell on here. I'm sorry, y'all. 67 maybe. So that would be a difference of 7. So then I would have a bar that's like that. So I'm hoping that you're getting the idea here. I'm basically needing to see how tall each of these go. Like what is this y distance right there? Like what's the y distance between this point and this point? And that is how tall my bars need to be. Let's take a look at number 15. We've got baseball salaries. Lidge's salary for the 2008 season was $6,350,000. So they want to know what the percentile is. So I would need to like look at this dot plot, which I'm actually going to make it a little bit bigger so that I can see it a little bit better. So presumably he is that dot right there. So I need to see how many dots are less than that. And after some quick counting, I found that there were 22 less than it. So that means like he's the 23rd dot. And there are 29 total I can see on this N here. So if I do the old definition, I would do 22 out of 29. But the new definition, I would do 23 out of 29 because it's actually on the 23rd. So 23 out of 29 will give me the percentile for the new one. That's the 79th percentile. So his salary was is it explain what this value means. So that means that his salary was either at or above 79% of the baseball players. Now, finding the z-score. Remember, z-score is always the value minus the mean over the standard deviation. So I'm going to do 6,350,000 minus the mean, which I can find right there, 3388617, and then divide that by the standard deviation, which is there. That's a pretty large standard deviation, wouldn't you say? And this ends up giving 0.79. Okay, that's a coincidence that they're both 0.79. They're not always going to be the same. Now, as far as what this means, his salary is 0.79 standard deviations away from the mean. That is what that means. Number 19, this is a good one about transformations. So we already have this summary data here for his class. Like these are the heights of his class in inches. And then he has the whole class stand on their chairs, which is 18 inches off the ground. So basically he's going to add 18 to every height. And he wants to know what's going to happen. So part A, find the mean and the median of these measurements. Because you're adding 18 to every single value, the mean is also going to go up by 18, and so is the median. Like they're just individual values. So I'm going to do, the mean is going to be 69.188 plus 18, and the median is going to be 69.5 plus 18. But then when we get to part B, it says find the standard deviation and the IQR of these measurements. Show your work. Here's the thing. Okay, you have to like imagine with me real quick. If I have a dot plot, let's suppose that I have this dot plot. If I take it, let's say that it starts at 0. Well, actually, I guess I'll make it look kind of like this one. So the minimum was 61.5 and the maximum was 74.5. Now, this is not necessarily his thing, but I'm just doing this for emphasis. If I take this whole thing and add 18 to every single value, this is actually going to be exactly the same dot plot. It's just going to start at 79.5. And it's going to go to 92.5. But it's the same shape, the same spread, everything just went up by that amount. So the standard deviation is not going to change. It's still going to be 3.20, just like it was in the table, because adding 18 just shifts everything. It doesn't spread things out. Same thing with the IQR. So remember, IQR is Q3 minus Q1. So I do 71 minus 67.75. And it's going to be, it doesn't matter that I added 18 to it because it's going to be spread out the same amount. Number 21 is referring to exercise 19, so I just wanted to keep it on the same page. He converts his original heights from inches to feet. So a conversion from inches to feet means he's going to divide everything by 12. So remember, all the numbers are getting divided by 12. That means like my original dot plot up here. The first thing I would do is add the 18, and then I would divide by 12. And so, or maybe he didn't have them, maybe he didn't add the 18 this time, but I would basically be taking this dot plot right here and squishing it. If I divide it by 12, the whole thing is going to squish. Everything is going to be divided by 12. So that means whatever the mean was is going to be divided by 12. Whatever the median was is going to be divided by 12. The standard deviation is going to divide by 12. And the IQR is going to divide by 12, because even the spread changes because it just physically gets squished by 12. Lastly, question number 23. This is also a good transformation question. So he uses a thermometer to measure different locations in the school swimming pool, and he gets a mean of 25 degrees Celsius and a standard deviation of 2 degrees Celsius. And then it's like, well, what if we actually change it to Fahrenheit? So y'all, we have to follow order of operations here. For the mean, if I multiply everything by 9 over 5, I'm going to have to multiply the mean by 9 over 5. And then I'm also going to add 32. So basically, like, I just end up doing what it says that I'm going to do. So I think that's 72 degrees. So my new mean is going to be 72 degrees, because means get affected by multiplication and they also get affected by addition. But as we learned from our last problem that we just did, the standard deviation, I don't care that I add 32, because the whole entire thing is going to shift the same amount, so it's going to be spread out the same. So the only effect that happens to the standard deviation is the 9/5. So I'm going to do 9/5 times 2 and get 3.6. So 3.6 is going to be my new standard deviation. I did not bother with adding because adding and subtracting does not affect standard deviation.